Lesson 12.1a on trigonometric ratios. Now, what is trigonometry? Trigonometry is a Greek word which can be broken down into two parts. The first part is trigon. Now, we're familiar with this term because we say it all the time, the word triangle. And the other part is meter, which means to measure. Trigonometry involves measuring triangles. In this trigonometric diagram here to the right, you can see that there's a few triangle graphics actually there embedded within that graphic. But the formal definition of trigonometry itself is the study of the relationships between triangle side lengths and their angles. Now, to understand the origins of trigonometry, we need to go back to the previous chapter and analyze similar triangles. Take a look at these two triangles for a moment. Are they similar? Why or why not? From the last chapter, we remember that when two triangles share two congruent angles, then we can conclude that those two triangles are similar by the AA similarity conjecture. Well, what does this mean? Understand and remember, what are two properties of similar shapes? Well, the first property is that all the angles are congruent. And the second, more important property when it comes to trigonometry is that all sides are proportional. So, for example, if I were to set up some side lengths here using some algebraic variables, the ratio in the first triangle between, let's say, the shortest length and the hypotenuse, say length A to C, or I'm sorry, A to B. The ratio between the two legs there in the smaller triangle A to B is equal to the same ratio between the two legs of the larger triangle D to E. And the ratio between the longer leg to the hypotenuse in the smaller triangle B to C is equal to the ratio between the same corresponding lengths in the larger triangle E to F. And ratio of A to C is equal to the ratio of E to F. All these ratios are equal because the sides are proportional, because the triangles are similar. Now that leads us to a very important conclusion. If you have a right triangle, say you're given one right triangle and a second specified angle, so two angles total in that triangle, then you can conclude that first, the triangle is similar to every other right triangle, larger or smaller, that has a second angle of the same measure. Just like in the previous slide where we had two triangles, one smaller, one larger, but they both had two congruent angles. And therefore, number two, every other right triangle with the same second angle must all have the same proportions. Since all similar triangles are proportional, therefore, anytime you have a right triangle with a second angle that's also congruent, it has to be proportional to every other similar triangle with the same second specified angle. And that leads us to trigonometric ratios. Ratios generated by specific sides of a right triangle. And the reason why these ratios exist is because in trigonometry, when we're given a second angle in a right triangle, then immediately those ratios are going to be consistent no matter what size of the triangle. So in this triangle here, if we were to label the side lengths A, B, and C, then we have three possible ratios we could examine. The length A to the length B, the ratio between the two legs, or the length B to the length C, or length A to the length C, the ratio between either leg and its hypotenuse. In fact, these three ratios here are the fundamental ratios in trigonometry, and they all have specific names to them. But to understand those names, we first need to introduce you to vocabulary involving the actual legs or side lengths in a right triangle. So given this right triangle and a second specified angle, there are three specific names of reference alongside this 12-degree angle. The first side that has to be named is the opposite side, and that's the side that's located opposite the second specified angle. The second length to be named is the adjacent length, and that is a side that's adjacent to the specified angle. And the third length needing to be named is the hypotenuse. Now, the hypotenuse is always a side opposite the right angle, just like back in chapter 9 when we studied Pythagorean theorem, where the hypotenuse was always the longest leg or the longest side opposite the right angle. Now, knowing these three side lengths, there are three primary trigonometric ratios. The first is the sine ratio, which is the ratio between the opposite side and the hypotenuse. Then the cosine ratio, which is the ratio between the adjacent length and the hypotenuse. And the tangent ratio, which is the ratio between the opposite side and the adjacent side. These are the three fundamental trigonometric ratios. Now, when you take the first letter in each of these parts and spell out a word, that word is spelled SOHCAHTOA. S-O-H for sine is opposite over hypotenuse. C-A-H for cosine is adjacent over hypotenuse. And T-O-A for the tangent ratio being the opposite over the adjacent. If you like this mnemonic for remembering trigonometric ratios, feel free to use it. Again, that was SOHCAHTOA, S-O-H-C-A-H-T-O-A. Now, let's get to some examples of using these trigonometric ratios. For example, in the following right triangle, where we're given angles A, B, and C, and then sides A, B, and C, where each side is opposite its specified angle. All the angles are uppercase, all the side lengths are lowercase. What is the sine ratio of angle A? Notice the notation for the sine ratio of angle A is listed as SIN space capital A. That's not sin, that represents sine, the sine ratio of angle A. Well, to find the sine ratio of angle A, the sine ratio is the opposite length over the hypotenuse. In the following triangle, the opposite length is side A, the hypotenuse is length C, so the ratio is going to be A over C. What is the tangent ratio of angle B? Well, the angle B up above has a side opposite it, side length B, and then has an adjacent length of A. Since the tangent ratio is opposite over adjacent, then the ratio is going to be B over A. Using some actual numbers, let's say that I give you this triangle where I give you some side lengths of 8, 15, and 17. What is the cosine ratio of angle B? Well, the side length adjacent to angle B is 8, and the hypotenuse is 17, so the ratio will be 8 over 17. And finally, what is the tangent ratio of angle A? Well, the side length opposite angle A is 8, the side length adjacent to angle A is 15, so the ratio must be 8 over 15. This concludes today's lesson.